We now want to talk about designing a system. The systems that we're thinking about are interactive. One thing depends on another, which depends on a third, and so forth, until it seems that everything depends on everything else. You're left with a problem. Where do you start? And how do you make sure that everything fits with everything else? I'm going to show you a very powerful approach that uses software that's available on everybody's PC. But to set the context of what the problem is, Mark, you were telling me a story about your experience of an Inmarsat 2.
Yes, this is what the story was that we were originally going to use a spacecraft bus that was being built at Bristol called Skynet. But it was not good enough. It was too old-fashioned. The technologies would not allow me to do it. So I had to work through, and it took me a week to go through each layer of management saying, look, I'm sorry, but we're going to have to use a version of our new sexy bus called Eurostar, and we're going to have to extensively modify it to do it, which is a big ask. On the other hand, Inmarsat was a very important project for the company. It was what the company was almost surviving on. So literally the last meeting I had with the senior board and everyone, and I got my decision that I could play around with Eurostar. So that was late in the evening. So I go into the office, 9:10, feeling completely and utterly washed out, but elated that I'm about to start doing the job. And through the door walks a thermal engineer and says, hello, I've just been assigned to Inmarsat 2. What does it look like?
At this point, you need to understand that the thermal design is almost the last thing you can do on a satellite. Working in the vacuum of space, the satellite has to get rid of any waste heat that's generated either by outboard systems by radiating away to deep space. That includes essentially all the power used by the electronic systems and anything else as well as the thermal radiation that's coming from the sun and the earth. Doing a thermal analysis requires not only knowing where the heat is being generated, but how much, and also what the structure looks like and what external surfaces are available for radiators and so forth. Expecting to have the thermal requirements ready to work on when all Mark had was little more than a blank sheet of paper was somewhat premature. But could we have done this differently? Could we have used system models?
To be fair, he didn't even give me time to get a blank piece of paper out of my desk. If you remember back to the first video, we introduced a concept of the system model with a warning that we would be introducing something called system models, plural, which are something quite different, and here we are. The system model is an abstract concept of interconnected elements that we use to cope with complex things. It is a model that can be in words or something like this diagram. System models are mathematical models of the system design, which are in themselves complex and systems in their own right, and which try to capture the emerging properties of the system being designed.
Returning to Mark's story, the thermal engineer wanted Mark's inputs so that he could do some calculations to come up with a valid thermal design. But if the numbers that Mark provided had been different, the same sums would have had to have gone through again to provide a different set of answers. So Mark could have given the man a typical set of inputs, but rather than just requesting an answer, he could have asked the engineer to write down, or even better, to put in a computer, the process by which he came up with these answers. Call that the model for the thermal subsystem. So when the right inputs become available, and as the design develops, it's quite probable that those right inputs will change again, the computer could repeat the task without further burdening the engineer. Of course, eventually the engineer would need to review the computer output to make sure that it still made sense. But in principle, we no longer needed to design a system in a particular order. And if we had similar models for the other subsystems that were contributing inputs to the thermal system, and we knew what aspects of the design were being affected by the thermal outputs, which are basically configurational issues, we would have a model for the whole satellite. And it doesn't have to start with the thermal system. We could have started anywhere and develop outwards, And as long as in the end we have component models for all the component subsystems and have them correctly connected together, we would have a complete model. And this is the basis of system modelling. When we start thinking about design, or even the components of the design, we start asking questions like, how big is it? How much power does it need? And what inputs are required for us to design it? A good engineer will probably begin by making calculations at this point. Very simple back of the envelope calculations initially, knowing that the more complex calculations are going to be required later. But if we join all the bits together so that the output from one set of calculations of one part of the system serve as the inputs to other parts, we have a model of the system as a whole, which will tell us how each part of the system fits together, and which can tell us about the characteristics and behaviour of the system as a whole. I talked about this already when I discussed functional analysis. Each component of the system acts to connect inputs from elsewhere to outputs to other parts of the system. In the old days it was done with scraps of paper and more formal reports, and the subsystem engineers, specialists, sitting around a table exchanging their answers, and the system designer trying to make things fit. And there were always mismatches between one subsystem output and the assumed inputs for another's inputs. Today it can all be done on a computer on a spreadsheet. The important thing about it all is that all the subcomponent inputs are matched to the appropriate outputs, and the intermediate calculations are representative of the expected behaviour of those components. The idea is that each of the subsystem models should be constructed in such a way that the subsystem expert can review their part of the model and sign it off. But it's no longer necessary for that engineer to do each iteration of the calculation personally. And the job of the system designer is to ensure that all the components are correctly linked together. Ultimately, this system model will allocate requirements to each of the subcomponents of the system. But being integrated within the complete model, we can change inputs or component performance and perform trade-offs, looking for things that would improve the system performance. And we will talk about what we mean by performance later. But I said that we start with simple back-of-the-envelope sums to size our component subsystems, and later, when we get a better view of what the system looks like, we will replace those simple approximate sums by more detailed calculations. So any method we use must make provision for us, or rather the subsystem experts, to change and upgrade the subsystem models as the design evolves. The quick and simple system model can be used to make early choices between different options, and also to indicate the areas where it's most important to have good information, more precise information or experimental data. Then, as we understand more and cut down on the range of possibilities, we can evolve the system model to include more detail. The general rule is to start simply with what you know and then evolve the model as you learn more. Another reason for starting simply is that at the beginning of a project we might very well have multiple possible designs to think about. We want to be able to compare different options, but not necessarily to do a detailed analysis on each one before discarding them. It's quite possible that some possibilities will not be more fine-tuning but of a single concept, but radically different ways of fulfilling the same requirement. But it's also likely that even with quite different designs, they will have many common components, even if these are used in different ways. By building quick, simple models which share the common component models, we can optimize each one separately and know that the approximate relationships in each model all work the same way. We can therefore compare and discard unproductive options at an early stage and concentrate on the initial productive possibilities.
Okay, Bob, let me just check that I've got the overall concept here. There will be a computer model of my system with the specialist pages for each of the major elements or subsystems, And these pages will be managed by the various members of my team. And as the system engineer, I will ensure that the links between these subsystem pages match those on the actual system design, and therefore reflect the functionality of the system, and hence reflect its emerging properties. And that's what makes it a system model.
Yes. Yes, it will become clearer if we look in more detail at what we expect it to do. If I were to list the requirements on a system model, it might look like this. A fully integrated system model should capture the mission objectives as they affect the system design. It should identify the system functionality needed to meet those requirements, make an explicit definition of the external interfaces, the environmental constraints and any safety factors and margins, and the data needed to define the requirements for the various component subsystems. The component subsystem models should predict the performance of those component subsystems and, by integration, the performance of the system as a whole, and identify relevant configurational issues. If possible, I would also like to include an initial estimate for the costs of the system, as this is likely to be important in later decision making. This may sound very complex. It might put the novice off from attempting such a task in the early phases of a design. However, if approached in the right way, it's remarkably simple. What we need is an approach which does not require the subsystem specialist to learn new programming techniques to create their part of the model. A way in which the subsystem specialist can read the calculations performed by their part of the model in a way they expect to see the calculations made and hence to review them. A format which allows the participating engineers to evolve their part of the model from simple back-of-the-envelope calculations to more accurate calculations as understanding of the issues involved develops. Similarly, a format where the system designer can check that all the component parts are connected together in the right way, and where they can extract appropriate system-level information on performance and configuration from them. Finally, that the model should be available to all members of the team to allow subsystem optimizations to be performed against system performance. This is why I use spreadsheets to build my system models. Specialist system modelling software packages are available, some originating within the software development community. But the more specialist these become, the less open they are to engineers who have not been in specialist training. Pre-packaged system models are like pre-packaged meals, very convenient at times, but ultimately not good for you. Now, everyone has Excel on their PC, and most engineers learn to use it. That means that the system model can be shared among the whole team. Individual sizing calculations will be written by the specialist in that area, and as a consequence they'll be laid out in a form they can understand and later approve. The facilities within Excel make it easy to trace where connections have come from, and if properly labelled, to edit or expand calculations as knowledge or understanding of the design evolves. Properly developed, the spreadsheet system model acts as a database for the whole project and can be shared among the whole team. This last bit means that some form of formal control over the system model is required, something that I will turn to later. The fact that the design calculations are laid out as the subsystem specialist would like means that once a calculation algorithm has been added to the model, if the input conditions change, the outputs will automatically be updated. This means that the subsystem specialist is not needed to re-perform their calculations every time changes are made. It does not even mean that the calculation processes have to be written in some logical order of connection. If the thermal engineer, to take an example, is about to go on holiday, they can provide a representative calculation algorithm, and that can be connected into the rest of the system models when the inputs are available. Of course, as the system design changes, each subsystem engineer will have to review their area of responsibility, but endless repetition of calculations are no longer necessary. And we are guaranteed that outputs and inputs between the component subsystems will always match. Here is a diagram of how the structure of a spreadsheet system model for a satellite might look. On the right-hand side, indicated in red, are separate sheets for each of the spacecraft subsystems, for the payload, the propulsion, control electronics and so forth. And on the left, I've shown the system level properties in blue, things like mass, cost and reliability, which build up budgets from the component inputs from each subsystem. And the left-hand side also includes top-down things that apply to the system as a whole, in this case indicated by a sheet labelled mission. What orbit is it going to fly in, how is it launched, and anything else. And there is one sheet labelled geometry, which is a bit of a special case. It's difficult to integrate a CAD package into a spreadsheet. It can be done, but it tends to limit the flexibility on both sides. But within your system model, the component subsystems will be generating geometric data in their own right. And it is useful to have a sheet collecting the sizes of things so that a CAD model can be built up in parallel. And then, when you've decided on an arrangement between the different parts, there will be geometric constraints identified, things like boxes occupying the same space, for example. Those constraints can then be added to the geometry spreadsheet to keep track of the physical size of the assembly and to be used to define the geometry of the supporting structure. So the geometry sheet acts as a useful interface with other design tools that we might use. I have advice on layouts which help make the model more readable and therefore easy to check. Even if it looks excessive, I allocate separate pages to each subsystem and organise each page to make it easier to find things. The calculation is annotated, which means that each number in the calculation is preceded by a label which tells you what it is, and is followed by the units. This last helps avoid errors of magnitude. Excel also has a comments facility which can be used if a short label is insufficient. Finally, we need to make everything in the calculation explicit. Rather than hiding the constants in a formula within the calculation, it's better to have an explicit line that says, this is the value I've used for G, for example. This means that I can use the same number wherever it appears. And maybe if we move the design to the moon and G is no longer 9.81 meters per sec squared, we have only to change one number. I also use colour coding for some lines, and I apologise at this point for any with colour blindness. There are other options for identifying special lines, like changing fonts, but they're not quite as useful. For most calculation, I use black, but then inputs are identified in blue, which tells the user this is a number that can be changed manually. We said the constants should be identified separately, and these are coloured in green to identify that they are inputs, but normally should be left alone. And finally, I use red to identify things you need to pay attention to, warnings or critical values. Purple was introduced as an editing age and should not appear in a completed system model. It serves two purposes. One is an input value. When we start, it means this is a guess that I need to be able to carry out this calculation. And when we know better from some other calculation in the model, it should be linked in and become a black number. The second purpose, which would normally mark an area in the calculation, is a reminder. This is wrong, it needs editing, and I need to come back to it. Let me show you how this works in practice. This is the system model for a rather simple communication satellite I use as a student example. This first sheet is simply a cover identifying what it is and where it comes from. In this example, there are a number of component subsystems whose size will depend on the overall mass of the satellite, but which in turn, those contribute to the overall mass, creating a loop. Here you can see how I deal with the problem. The blue number is my guess as to what the mass is going to be at the end of the estimate, and below it is the red number is the model estimate for what it thinks the total mass is, and these two have got to be the same. So if we make the blue number the same as the red number, then the loop is closed and everything fits together. You'll also notice on this sheet that I've started a mods list, a modification record showing when and why each issue of the spreadsheet has been made. This is important when we come to think about how such models are managed within a larger project group. Being a communication satellite, the first thing we need to know is where the satellite is and how far away the receiver footprint is on the ground. This is going to be part of the mission definition, so we go to the mission sheet, and you'll notice first that at the top here we have a number of characteristics of the Earth around which it's going to orbit that we need to know, and these are marked in green to show that they are fixed constants. Below it we have a calculation of the characteristics of geosynchronous orbit where the satellite is going to reside, and below that a calculation of the range and footprint with a series of blue numbers which are inputs to define where the satellite is going to be, where the target area on the ground is relative to it is, and the orbit in which the satellite is going to be placed by the launch vehicle. And at the end of that we have a range and a beam width, and we also have from the orbital data a delta V requirement that the satellite propulsion system will have to give when it inserts it into orbit. Now that we have numbers for the distance between the satellite and the area on the ground we want to illuminate, we can start to put together a communications link budget for the transmission from the satellite to the ground. This will define the size of antenna we need on the satellite and how much RF power we need to put into the beam. This is a standard link budget calculation straight out of the textbook, progressively working through the losses which take place between transmitter and receiver, with design inputs for the frequency that we're transmitting at and the ground antenna characteristics. And at the end we have a signal margin at the bottom here. There will be a similar link budget for communication between the ground and the satellite, and eventually there may be parallel estimates for the best and worst case transmissions. In this case it appears that we need about 60 watts of transmitter power from the satellite. Unfortunately, travelling wave tubes that provide this RF power come from a number of set sizes, and so we have to choose the next largest example, which I programmed into this spreadsheet automatically. Then over here on the right hand side we've got a table which assembles all the communications equipment we need with their masses and power requirements and any other data that we might feel useful later. We now need to feed this power subsystem requirements alongside the power requirements for any other user subsystem on the satellite. The first thing that we meet on this sheet is a power budget, sitting up here in the top left hand corner. As usual, there are multiple power budgets, one for when the satellite is in sunshine, drawing all its power from the solar rays, and the second when it enters the Earth's shadow and is in eclipse, and a third one when it's on its transit up to orbit. To make calculation on how much battery charging we need to know how long the satellite will have to survive in eclipse. And so we go back to the mission sheet and add a small calculation to estimate how long the satellite will be in shadow and transfer this into the power sheet here. The power budget then sizes the solar arrays and the onboard batteries. These could have been very simple numbers to start with, but will later be replaced by more detailed calculations as shown here. Note that there is also a defined power margin, actually an array margin, applied to the budget calculations, and a consequential thermal load estimate. Yes, that's part of the eventual thermal calculations, since all the power brought onto the satellite must eventually appear as heat, apart from that small fraction going earthwards in the RF beam. I'll show you one more sheet here. This is for the propulsion subsystem. The propulsion subsystem is important because it has a significant effect on the eventual satellite geometry. In this case, the left-hand column here goes through the various manoeuvres that the satellite must undertake and calculates how much propellant each will require. There are margins here defined by increases in the performance demands of the various manoeuvres, plus a 2% residuals value for the fact that you can never empty a tank completely. Then to the right, we have calculation of the size of the tanks that we require and other propulsion equipment, data on the main engine and the RCS thrusters are input as design decisions, but we could do comparisons of different thrusters here by changing the input values in these tables. The tanks are large objects within the overall satellite structure and as such affect the satellite geometry and other features such as the structure and external surface area. So the tank size data gets fed into the geometry sheet. This is the geometry sheet, and the first thing to consider, besides simply collecting data on the dimensions of the various components, is the width and radial dimension of the box that forms the outer surface of the satellite, which is set by the need to package things inside it, in particular the propellant tanks. In fact, there are no less than 3 factors which could set the size of this box, and the model selects the largest of these 3 factors, shown here as half-width constraints, so getting an outer panel width that doubles it. The second thing that we need to consider is the overall height of the box, which we get by adding the stack of components that generate this dimension. Note that we include margins, in this case, in the form of clearances. With these 2 values, we now know the principal dimensions of the structure of the satellite. And given component masses and the launcher loads, we can do approximate calculations on the necessary strength and rigidity of the structure.
The capabilities of the spreadsheet geometry shown here are not sufficient to fully assess the geometrical aspects of the system. As Bob said earlier, this is intended to actually be linked to a CAD geometry model in a different software package. Here is such a CAD model with a very small satellite. The model was originally used to see if a usable satellite could be fitted within the volume constraints of the CubeSat standard, but as the project evolved, it became the basis of the final design and then the way in which we created 3D printer files for production of the structure. The constraints of geometry on a system are numerous, and these constraints are often not easily packaged into simple formulae that can be put into a spreadsheet. In Bob's example, there are many assumptions about the geometry of the spacecraft which have been hardwired into the spreadsheet, such as the arrangement of the tanks. And it has no real ability to deal with the real physical configurational problems. In geometry models like this, there is a complete freedom to explore options available and cope with their complexities. Now, it is possible to have CAD programs read information off Excel spreadsheets, although this does require a bit of software expertise to manage. The problem is getting the geometry model to report back to the spreadsheet in a way the spreadsheet can use. So the spreadsheet, for example, can tell the CAD that there is a tank with this size and simple geometric shape and even its location. But if the CAD model then moves the tank or makes the shape more complex, it is difficult to tell the spreadsheet model other than by some hand input into the relevant cells. These geometry models can do many things that spreadsheets cannot. For example, they can accurately assess the mass of complex shaped components. And I have seen this when we made the structure of this satellite with a 3D printer. My electronic scales could not measure the difference with the CAD model's predictions. and they can also be used directly as an input to full finite element structural analysis, thermal analysis and computational fluid dynamic analysis. And they can also be used with models of people to assess human factors issues. And just as the spreadsheet model can grow in complexity following the evolution of the system as the project progresses, so can the geometry model, checking interference, field of view, tolerances, and the centre of mass of the system. In the production phase, they can be used as the direct basis for manufacturing drawings of many components, particularly in the structure. Now, in many ways, these geometry models look like system models. All the elements of the system are here, held in proper relationship to each other, and many of their properties are included in the model. But what is missing is the interactions between those elements, so it can not model the emergent properties of the system, so it is not by itself a system model. But it can be an important part of an overall system model if just a little semi-detached, as at the moment, as we've discussed, geometry models cannot be completely integrated into spreadsheets. So there will have to be some hand transferring of data between the two. It will also be used to be generating inputs for the structures page, as structures are heavily dependent on the geometry of the system they are supporting.
Here is a set of calculations on the structure. For the moment, I've treated each component of the structure individually. Eventually, we will use geometry to do finite element analysis of the whole structure. But while the geometry is still evolving and we're doing trade-offs on the design, building finite element models each time will be a waste of effort, and approximate methods like this are satisfactory. So finally, everything gets integrated together in the mass budget. Here all the components are listed subsystem by subsystem, with the model estimates for their individual mass and with an approximate component margin added as in the previous lecture. And then if we go down to the bottom of the table, having got an estimate for the total dry mass, we add an additional dry mass margin to get the total dry mass, plus the propellant to be carried to get the overall satellite mass. And that closes the loop we saw on the first page. Since we now know what the dimensions of the satellite are, and thus where the components are located, we could add to this table by doing further calculations, such as where the centre of gravity is located, what the principal moments of inertia are, and so forth. And we can also use the mass data to do parametric cost estimates to get a first idea of the cost of the satellite. I have said that the individual subsystem calculations should be the responsibility of the subsystem engineers and signed off by them. However, when we do many similar designs, it's possible to isolate the individual calculation algorithms, make a library of them if you like, and reuse them in future projects. This allows us to progress from very simple calculations to more detailed models very quickly. We can use a similar process in the early stages of design where we want to look at different similar but not identical options, where we can keep most of the basic model identical but just change the parts that are different. The numbers may change, but the relationship and assumptions are maintained, and we still compare apples with apples. System models will therefore evolve, starting with simple components and general relationships, and developing complexity in easy stages as the design itself evolves. In this respect, it acts as a database for the whole design, which is why it should continue to be available and relevant to the whole design team. Making subsystem designers responsible for their page in the model is one way of achieving this. Subsystem models can be checked, validated by reference to more detailed analysis and by being checked against known designs or past experience. The system designer then has the responsibility for making sure that the correct input connections are made between the various parts of the model and that the model is complete with something in it for all components. But this then brings up the issue of configuration, management and control. The major problem about using spreadsheets and then making them generally available to everyone on the project is they're too easy to modify, and everybody knows how to do it. So that within minutes of receiving a copy of the system model spreadsheet, one of your subsystem engineers will have already seen something that needs altering and had a go at seeing what that change would do to their component. And so in no time at all, there will not be one spreadsheet model, but as many as there are engineers working on the project, each with unidentified differences from one another. To avoid this catastrophe, it's necessary to introduce configuration control management into this process. This involves having one master spreadsheet held by one individual, normally the system designer, and modified by a traceable process. Copies of the master spreadsheet can be made available generally and experimented with at will. Modification of the master, however, requires a formal process. Anyone wanting to propose a modification, an update, to the system model, that is to the design itself, will then need to bring it to the configuration meeting. And there it can be reviewed, accepted, minuted, and used to produce a hopefully improved version of the system model master. This is why the front page of the spreadsheet carries an issue number and a short record of what the changes that have been made. Such a meeting does not have to involve everybody on the project, only those involved in the changes, as long as the minutes are generally available. But by having regular configuration meetings, not only does the system model represent a faithful representation of the state of the design, but it also allows the chief designer to follow and direct the stated development of the design. The system model configuration control then becomes an important management tool for the project. In the model-based design process, the subsystem specialists contribute models of their subsystems to the overall system model. Because the submodels are linked to one another and in the correct relationship one to another, the model design is always internally consistent. System reviews are therefore concerned with whether the model is adequate, produces a design that can be built, and trade-offs can be conducted at system level, and alternative concepts are evaluated on an equal basis. Cost estimating can be included in the system model and be used to optimise the system. Properly controlled, the model encapsulates the state of knowledge about the system at any time. The model review process keeps the manager aware of progress on achieving design understanding, and project managers, system designers and subsystem specialists can all see day to day what is being assumed. The model may also be used with the customer to trade requirements and find an acceptable solution where they can appreciate the impacts of demands. And the prime team can be kept small, concentrating on the system trade-offs and the configuration control.
Spreadsheets are not the only way to produce system models. As an example of an alternative, BAe Systems at Wharton has developed a specialist program called CAPS, which is a system modelling tool used by their design team for fighter aircraft studies. It was used on both the Tornado and Typhoon development programs. The program contains many separate modules handling different aspects of the aircraft: engine performance, aerodynamic qualities, control surface sizings, etc. And this is combined with overall models for aspects such as mass, flight performance. And these all interact with each other, so the program can be run to establish an optimal configuration for a given set of parameters. This could be used for the advanced study group to quickly explore different approaches using the standard modules. If the study went further, these standard modules could be replaced with specialist, more accurate models. So as the design decisions were made, the model became more detailed and refined, guiding the design team to the optimum system configuration. In the 1980s, the Wharton team was leading the HOTOL spaceplane project, and they used CAPS to explore the launcher's configuration. Although no one outside the study seemed to notice, HOTOL's shape was constantly altering noticeably. CAPS was being used to determine the optimum length that balanced the impact of the aerodynamic drag and the structure weight. And it was only towards the end of the study that this modelling had been validated enough to give confidence in the results. Well, since we brought up CAPS, I know that that was used on the hotel project quite extensively, so you have experience of it.
Yes.
As I understand it, one of the key features of it was that the various elements within the program were rather like your spreadsheet, specialist spreadsheet thing, that you could pull out a module that was the jet engine power,
Yeah.
or whatever. How did it work?
Well, yes. You have to remember that CAPS was originated back in the 1960s.
Yeah.
So it was, from a software point of view, slightly clunkier, with it being fair to it.
Even by 1980 standards. Yeah.
And it was pre-spreadsheet era. But it worked as a system whereby the structural and design would go into there, and the engine design would go into there, and the aerodynamics would go in, and so forth. And you would feed them all together, they would interact, you'd tune the numbers and come out with an optimized design, and then you look at it and say, why has it done that?
Yes.
And
Because some of them didn't look very
things.
optimised when
Yes.
they came out.
But it was, quite often, it showed you something that was funny in the design,
Yeah.
that when you spotted it,
Yeah.
then somebody would go back and change this little bit of structure or that.
What sort of cycle time did you have on it?
And that basically took about 2 months to cycle that round. It demanded, we didn't have a spreadsheet, we had a guy called the performance engineer, Steve Furness in our case, who acted that way, who put everything into the program that the specialists had put together, played around with it and came up with an answer, and then we
So
had
you've got a
another
little
guy.
bit of this master of the software problem.
Yes.
Yeah.
He wasn't, in fact, he was the dog's body rather than the system designer
Yeah.
in many respects.
But a bright guy.
He was bright, yes, but it was a junior post, let's put it that way. Now, in the early 1990s, when Hotel was in my past at that point, and spreadsheets appeared on PCs and so forth, and I started playing with them, I realised that I could do most of our spacecraft design in the CAPS fashion on a spreadsheet. In fact, it was quite nice because there is kind of a standard guidebook on spacecraft design. This Bible, Space Mission Analysis and Design by James Wirtz and Violet Larson.
Yeah.
And the great thing about this is that he goes through all the different systems and not only tells you about them, but tells you how they're designed.
Yes.
And
indeed, some small satellite project from new teams have
The-
used that as the
that's
Bible
right.
and gone through.
There was, in fact, a background thing. And so I started within our organisation to try this out on different things. And there was an ESA conference in the middle of this on system design technology, which was quite interesting because lots of people were trying to develop bits of software that would do system design. They were all specialist bits of software. And I went along to this meeting and I gave a paper that said, hey guys, you can do all this on a spreadsheet. And as it happened, my chairman at that meeting was Professor Larson, who was co-author of the book. So I said, basically what we've done is to put his book onto a spreadsheet, right? Because I was a contractor and so forth, this went down... And British. That went down like a lead balloon that day. However, the following day, Jet Propulsion Laboratory, JPL in America, came in and gave their paper, and they said, hey guys, you can do all this on a spreadsheet.
Moses has spoken.
And in fact, therefore, I can't claim that this is my methods. It was invented more or less simultaneously by JPL, who had more money than I did, the Aerospace Corporation in America, independently of JPL, and ourselves. And incidentally, some years later, when I talked to people at Wharton about CAPS again, I discovered that they'd basically torn out the centre and run it on a spreadsheet for CAPS as well. So it was kind of invented separately. And we tried it on a number of small studies, and then I got it.
Just to say that independently again, it's so obvious that I was doing it for my own projects. I think what's unique about what you're proposing is the configuration control that means that a team can do it rather than just one person.
And that basically came because of the first real thing that I was involved in.
Yes, which is.
But back in the
this mug you keep serving me my coffee in mentions Euromoon core team.
We had a project run at ESA called Euromoon, which was supposed to be a fast track development of a lunar lander, of an unmanned lunar lander, and I got seconded onto this and became one of the two chief designers initially. And because I now knew how to do it, we used the spreadsheet as a method of developing the project. And when I talked about it can be used for very different designs, initially we were looking at everything from a 4-kilogram hard lander up to a full Ariane 5 full load of equipment, so anything in between, and we're looking at all of them, comparing them, and then firming up with the design. And a lot of the ways of handling it, the management in particular, came out of that project, because we had to learn about how you design the model, how you managed it, how you exerted configuration control on it, for example. And we were learning on the spot, but one of the ESA engineers assigned to the project, Massimo Benedicci, who was sort of my level in this, was kind of looking over my shoulder and said, "Hey, why don't we always do that?" And out of that came what became the standard thing of what they call a concurrent design facility, where everybody has an input to the spreadsheet and everything goes together. It doesn't quite work exactly the way that I do, but it works for ESA, and uses spreadsheets as the basis of the thing, with a readable format for each of the subsystems and interactions controlled by the system designer.
So it's a technique that has been proven in anger in real projects.
Yes. And not just me. Effectively, you probably work on the basis that both American and European projects now run something very similar to this. But the advantage is that you can also use it in teeny tiny projects like group design projects.
In the 1990s, a unified modelling language, or UML, was created as a tool for software development. A modelling language is a general term for artificial languages that use a defined rule set to create an analysable model, either through graphics such as flowcharts or the formulistic use of words. Between 2001 and 2005, a specialist variant of the UML was created that was more appropriate to the general system engineering requirements, and this was called the Systems Modelling Language, or SysML. It was then supported by Nkosi and is now an open source standard that can be used by anyone. It is primarily a graphics-based language using interlinked diagrams. So, for example, a requirement in the requirement breakdown diagram, such as produced by DAWs, would be looking for a function in the function breakdown diagram and an element in the system diagram, which would have properties that were derived either from direct input by the user or from some parametric diagram or model embedded in the program itself. An example of a commercial product using it is Cameo Systems Modeler. The SysML and the programs like Cameo have the same relation as English and Microsoft Word. SysML is part of a movement towards trying to incorporate the systems model as the main design tool at the heart of the system development, rather than just a supporting and analyst tool. This is called model-based systems engineering, or as Bob has already called it, model-based design processes. The vision is that everything from the requirements breakdown to the system design of all the elements and interfaces is included in one giant model that will produce the requirements and other documentation through to the design instructions such as drawings, manufacturing procedures, even 3D printing files, and then it will go on to produce the test procedures. The objective being that such a model would ensure that everything would be consistent and the complete system-wide impact of any changes could be instantly assessed. A second advantage is that the level of analysis that can take place at any stage can be more detailed and comprehensive, or looked at another way, the detailed analysis can be done earlier in the development cycle. I think there are several conclusions on model-based systems engineering that we can draw. Using spreadsheets is an almost obvious way of doing things, and what Bob has outlined is definitely an approach for concept, feasibility and early system designs, enabling faster exploration of ideas and providing a more reliable and complete system design at the end. However, the full specialist packages like Cameo have more rigid structure, and I feel suffer from the same problems as the requirement packages like DAWs. The program with its input requirements dominate the system design process and get in the way of the organic process of evolving system design. Would you agree with that, Bob?
Yeah, I think that the issue, first of all, I don't really see why I should spend a lot of money on a specialist program which limits my capability when what I've got is an open and readable system that costs me nothing at all to set up. And I feel that openness and accessibility is a key issue that goes into all these things. That's one of the reasons why I emphasise that the system model should be available to everybody, and it should be written in a form that can be read. Don't hide things.
Yes.
Some of the time that may seem extra effort, but it means that we understand what's going on.
Yeah, and at the early stage of a project, when you've got a team that may be 5 to 10 or something like that, it's the big communication tool about what everyone's doing to one another. And another important point I think on your system is that because your team is the one that built it up, everybody somewhere in the team understands everything about the thing. It's their input into the system. It's not being imposed upon them by this outside piece of software.
Yes, everybody is bought into the system.
Yeah.
It's their own sweat and blood, if you like. And you may be using pre-packaged units in it. If you built it up as a whole, then you'll have a library of things you can plug in together and so forth. But they're written in a way that the specialist engineers can look at that and say, yes, I understood what happened there. And the fact you're getting a funny answer at this end is probably because you've got a funny number in there somewhere. And that means that you can sort the problems out. And because it's a database, it can feed all the other things you need to feed. It feeds you the dimensions, it feeds you the stresses, it feeds you the forces and so forth as part of the package. So it's moderately easy to link it up to other things, to finite element analyses and CAD programs.
To be fair to things like Cameo, they're supposed to do the same thing, but they're much more imposing a structure on how to do it and the point you do it and everything. For me, I think the real breakthrough in the future will be when things like Cameo become much more like your spreadsheet program, and that they fully integrate with the 3D design packages. So that once you've got that seamless integration of probably a okay, it's a bit of Hollywood. But when you look at Tony Stark in his laboratory and how he's designing and making things, that is a sort of the almost fantasy version of this completely seamless 3D modelling and database and system modelling.
But you see, he asked his computer.
Yes.
Right. I asked my subsystem designer, why has it done that, Fred? And I get an answer from him.
I think, to be fair to the film, the premise is that he's so clever.
Well,
he's written the software.
And his computer answers. And
yes.
One of the major problems with AI in general is it does funny things, and you can't say, why has it done that?
No.
Whereas when you get a good system and that says, I don't think we should do that because I've got this explanation, then you've got the interactions you want. You've got the relationship with it.
Well, Bob, it's not going to be you and me, it's going to be the people who are teaching now who are going to have to address that one. So that's something to look forward to in your career.
Yes. In summary then, a good system model provides a key tool in the system designer's armoury. The model links all the component parts of the system together, identifying the relationships between the different parts and allowing the rapid redesign as the system evolves. Early models can be built from standardised parts, allowing for a quick evaluation of competing possibilities. Then, as an understanding evolves, the model can be evolved in line with that understanding. Spreadsheets make this process relatively easy and can be understood by everyone on the project. The model then acts as a database for the projects, and it can then be used to input data to, for instance, finite element analysis programs and system simulators as the project advances. But more than this, the system model can act as a management tool, allowing the chief designer to keep track of progress among the various subsystem designs. And the good news is the software required is available on everyone's desktop computer.